Hi there, Andy here. So today I want to talk to you guys about atoms and energy levels. Let's start off with how to describe an atom. Firstly, we have the chemical symbol, and this is kind of the two-letter designation we use to describe different elements on the periodic table. Here we have Cr, which is chromium, and as a superscript, chromium is going to have 52. This 52 represents the atomic mass number. And then as a subscript, we have 24. And 24 is the atomic number. So the atomic number is known as Z, whereas the atomic mass number is A. The atomic number is basically how you describe the identity of an element. And in this case, it's 24, so there are 24 protons. And so the identity of any element is defined by the number of protons. So identity defines element. If we had a different number, say 20, it would be a different element, and I think in this case 20 is calcium. So we also have this number up here, the atomic mass number, and the atomic mass number A is simply the number of protons plus the number of neutrons. And so it's kind of the whole mass of the atom. Now, as you probably know, we have protons, neutrons, and electrons, but electrons essentially have no mass, so we don't need to add it to get the atomic mass number. So if you were to look at this element and you wanted to find out the number of neutrons, what would you do? You would just subtract the atomic number, which is Z, from A. So number of neutrons would equal A minus Z. So when we talk about neutrons, they themselves do not define the identity of an atom, and they can be different for each atom, and we call these isotopes. So isotopes are when you have different number of neutrons for each atom. So in this case, in the case of chromium, in our example we had how many? We had 52 as our atomic mass and 24 as our atomic number, and so we could easily have 53 and 24, and this just means that there's one additional proton, or excuse me, one additional neutron, because if we were to have an additional proton, if this were 25, now it's no longer chromium, it would be manganese. So isotopes can differ per element. And so let's briefly talk about our last thing we mentioned is the electron. And so electrons, you're going to have the same number of electrons as protons if the atom is neutral. What do we mean by neutral? That's just talking about its charge. So as long as it's not positive or negatively charged, you'll have the same amount of protons as neutrons. And so what happens when these things are charged? Well, we have ions. So if they have a charge, they're called ions. And there are two types of ions. There are cations, when the element has a positive charge, and there are anions, when the element has a negative charge. So if something has a negative charge, it has more electrons, and when it has a positive charge, there are less electrons. Okay, so just to be sure, these neutrons and protons, they're collectively referred to each other as nucleons. Protons and neutrons, because they're located in the nucleus. So I'm going to draw an atom for you here. And let's draw it for nitrogen. So nitrogen is going to be N is the symbol, 7, or the number of protons, or the atomic number, so Z equals 7, and then its mass number is 14. And so how do we get the number of neutrons? It would be mass minus atomic number, so it's 14 minus 7 equals 7. So there are the same amount of protons and neutrons in this isotope of nitrogen. So I'm going to draw the protons in orange. So we're going to go 1, 2, 3, 4, 5, 6, 7, and then I will draw the neutrons right there in blue. 1, 2, 3, 4, 5, 6, 7. So they're referred collectively as nucleons because they're in the nucleus. Now, what else is in our atom? We have electrons. So these electrons will not be found in the nucleus. They will be found around the atom in what we call orbitals. So each of these kind of spheres, remember because this is 3D, but I'm drawing it on 2 dimensions, each of these spheres kind of revolve around the nucleus. And this is not to scale. A good way to think about it is if the nucleus is the size of a golf ball, then the entire atom is the size of a football stadium. So this is obviously not to size, but we're just drawing it here. So keep that in mind, that the nucleus is a really small portion of the entire atom, and almost the rest of the stadium is full of electrons running around in these different spheres. And so these are each called shells. Okay, so each shell is associated with an energy. So associated with energy. And so let's draw on our electrons. Since this is a neutral atom, our protons equal our electrons. So we had 7 protons, so we're going to have 7 electrons. In the first shell, only 2 electrons can fit. And then in the second shell, we can fit the next 5. And so this, we'll call this n equals 1 for the first shell, and then n equals 2. And so I briefly want to discuss this. Since each shell is associated with a different energy, we can compare the different energies as they change between the shells. So if we draw kind of this diagram where we have increasing energy going up, our first shell, let's say it starts right here at n equals 1. So it's a pretty low energy because it's the first one. And as we go up, let's say the second shell is right here, n equals 2. And then the third shell is right here, n equals 3. And then let's say n equals 4 here. So notice what we drew here. The area, or the distance between, let me use a different color. The distance between each shell is the change in energy, right? So as you go up to higher shells, you're at a higher energy, right? Because you're higher up. So let's say this is 20 or 10 joules, and this is 2 joules. So you're at a higher energy the farther you go up, but the space in between each energy level is smaller. So let's write it like this: the energy from a change in the second level to the first level, so from here to here, is greater than the energy change from the third level to the second level, from here to here. So you see, as you go farther up, the differences in the energies for each shell, each distance we get away farther from the nucleus, decreases. The overall energy, this 10 right here, is of n equals 2 of the second shell. It was still greater than the n equals 1 energy, but the distance and the change in between them decreases as you get farther away from the nucleus. And we'll explore this idea a little later on.